ಇದು ಮಾಹಿತಿ ಖಜಾನೆ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿ.
ಮಾಹಿತಿ ಖಜಾನೆ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿಗೆ ನನ್ನೆಲ್ಲ ಸಂಯುಕ್ತರಿಗೂ ಆತ್ಮೀಯವಾದ ಸ್ವಾಗತ. ಇಂದು ನಾವು ಮತ್ತೊಂದು ಉಪಯುಕ್ತ ಮಾಹಿತಿಯೊಂದಿಗೆ ಬಂದಿದ್ದೇವೆ. ಈ ವಿಡಿಯೋ ನಿಮಗೇನಾದರೂ ಇಷ್ಟವಾದಲ್ಲಿ ಲೈಕ್, ಶೇರ್, ಕಾಮೆಂಟ್ ಮಾಡಿ ಹಾಗೂ ಇನ್ನೂ ಹೆಚ್ಚು ಉಪಯುಕ್ತ ಮಾಹಿತಿಯನ್ನು ನಮ್ಮ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿಯಿಂದ ಏನಾದರೂ ನಿರೀಕ್ಷಿಸುತ್ತಿದ್ದೀರಾ? ನಿರೀಕ್ಷಿಸಿದಲ್ಲಿ ಬೆಲ್ ಐಕಾನ್ ಅನ್ನು ಕ್ಲಿಕ್ ಮಾಡುವುದರ ಮೂಲಕ ಸಬ್ಸ್ಕ್ರೈಬ್ ಆಗಿ.
Chandrayaan 1 3D view of moon crater depth 400 m terrain mapping camera SM resolution area 10 by 10 kilometers date of pass 23rd November 2008 craterlet Beroich HYSI 6 to 12 8 to 13 6 to 15 6 to 19 B 26 to 21 836 BJE 8 to 41 842 843 8 to 44 8-458 46 8 to 19 B 51 6 to 43 845 868 to 60 to B 24 6 to 32 6 to 56 1 10. Photogrammetric modeling and data processing. Chandrayaan 1 perspective for linear CCD imaging sensors by B. G. Krishna GD, SPDCG, SIPA, SAC. Photogrammetric modeling and data processing. Chandrayaan 1 perspective for linear CCD imaging sensors B. Gopala Krishna, Sanjay Singh, TP Srinivasan 1. 0 Introduction SPDCG SIPA Space Applications Center Ahmedabad. Photogrammetric modeling is an important aspect for any planetary mission dealing with mapping of the planetary surfaces with respect to topography using imaging sensors. This basically includes the derivation of precise relationship between the obtained image and the planet's surface, ground, and the derivation of topography. These models further help in correcting mapping this imagery onto the surface, like orthomage generation, after eliminating various distortions due to camera tilt, planet rotation, curvature, satellite motion, surface relief, etc. The basic inputs required for sensor modeling are sensor parameters, mission parameters, satellite ephemeris, and other ancillary data. Control points, if available, further improves the model parameters, making the relationship image to ground to image more precise. This needs an appropriate mathematical formulation to update the model. In the planetary data processing, the ancillary data including the ephemeris are generally represented in the form of spice kernels 12. This tutorial addresses the photogrammetry model and data processing aspects of Chandrayaan 1, 2, 3. CCD line scanner imaging sensors terrain mapping camera, TMC, and hyperspectral imager, HYSI. 2. 0 Photogrammetric model. As indicated in the previous section, a major task in correction of line scanner imagery, in the case of Chandrayaan 1, is to establish a relation between image and object space, lunar surface. There are various ways to achieve this. Rigorous imaging model based on photogrammetric collinearity condition has been adopted for Chandrayaan 1 to establish the view direction. 2. 1 Collinearity condition. The relationship between image and corresponding object space coordinates is established through physical imaging model in the form of collinearity condition. It states that the perspective center, image point, and the corresponding object space point all lie in a straight line. Mathematically, it can be stated as 2. 1. ZXA XS is equal to S asterisk M asterisk Y is ZA Z is 1, where X, Y, Z are image focal plane coordinates of an image point, S is a scale factor, M is the transformation, rotation, matrix between object and image space, XA, Ya, ZA are selenocentric coordinates of a ground point, XS, Y is, Z is, are selenocentric coordinates of the perspective center 3. 0 coordinate systems. In order to establish a precise relation between any two coordinate systems, it is first necessary to consider and list all the coordinate systems in use. The definitions and conventions for each of the above coordinate system are strictly adopted specific to Chandrayaan-1 convention. The following standard coordinate systems are used to carry out the required transformation in the imaging model. The same concept can be extended to any other planetary body. 3. 1.1 Inertial Coordinate System, LCI. Lunar-centric inertial system or selenocentric. This is a lunar-centered system with moon's center as origin. This system is parallel to geocentric inertial coordinate system whose x-axis is towards vernal equinox of date, epoch 2000, y-axis perpendicular to x-axis in the Earth's equatorial plane, and the third axis completes the right-handed triad, Earth's rotation axis. 3. 1.2 Lunar-centered lunar-fixed selenographic system. For LCLF, moon's center is the origin. X-axis is taken in the moon's equatorial plane pointing towards the moon's prime meridian, which is chosen so that it is on an average directed towards the center of the Earth's disk. Y-axis is perpendicular to x-axis in the equatorial plane of moon, while the third z-axis is directed towards the lunar axis of rotation and completes the right-handed triad. The two angels, figure 1, necessary to define the position vector in selenographic coordinate system are defined as follows. 4m, selenographic latitude, is the acute angle measured normal to the moon's equator between the equator and a line connecting the geometrical center of the coordinate system with a point on the surface of the moon. AM, selenographic longitude, is the angle measured towards the west, in the moon's equatorial plane, from the lunar prime meridian to the object's meridian. 3. 1.3 Orbital coordinate system. The definition is as follows. At any instant of time, spacecraft x-axis towards moon center, your z is along 2 way orbit normal perpendicular to x-axis in the orbital plane, and the third one, y-axis is perpendicular to both x and z, x direction, RRL, z direction, RXV vertical bar, RXV, and y is cross product of x and z. Moon's prime meridian meridian. North lambda. X moon's equator figure 1 selenographic coordinate system. 3. 1.4 Body coordinate system. Body coordinate system is nothing but orientation of orbital coordinate system for a given pitch, roll, and your angels. This coincides with orbital coordinate system in the absence of roll, pitch, and your angels, all of them are 0. 3. 1.5 Image plane coordinate system. Image space. This is the focal plane coordinate system where f, focal length, is in the direction of positive your x direction, z is along the detector array, and y is perpendicular to the array. 3. To estimation of image coordinates from ground coordinates. The sequence of transformations, which are considered for computing the image coordinates using ground coordinates as the input, are as follows. A. Given latitude, longitude, and height of a lunar point, it is first converted to Cartesian, selenographic system, coordinate system. B. Transformation of selenographic coordinates to selenocentric coordinates, using the liberation angels from JPL ephemerides. 2. 3. C. Selenocentric coordinates are transformed to orbital frame of reference using state vectors. D. Transformation of orbital system coordinates to body frame coordinate system using the attitude, orbit to body. E. Body frame coordinate system to sensor, imaging payload, using the spacecraft mounting angels and alignment angels. F. Sensor frame, imaging payload, to image plane or focal plane coordinate system using the payload geometry of TMC or HYSI. G. Focal plane coordinate system to image coordinate system, scanline, pixel. Transformation matrix M consists of 4 rotation matrices. M is equal to Rn asterisk Ra asterisk Rho asterisk Rlib, where Rlib is the rotation matrix for transformation from selenocentric coordinate system to selenographic coordinate system. These two coordinate systems are oriented by the Euler angels, is and are relative to each other as shown in figure 2.13. N is Y. Z ecliptic lunar equator X. N Y ecliptic Y. Earth's orbit gamma. X ecliptic figure to selenocentric and selenographic coordinate systems. Therefore, RLIB can be further decomposed into three matrices. RLIB R dot R I R 2 4. Determination of Euler angles R and A involves Moon's mean orbit because of the relationship between Moon's mean position and the orientation of lunar selenographic coordinates. Above figure shows ecliptic plane, zecliptic, yecliptic, which passes through the center of the Moon. The lunar equator and orbit planes are shown intersecting in a line on the ecliptic plane. The XM axis is shown in the lunar equator. In this Moon relative coordinate frame, the Earth is considered as orbiting the Moon, origin, in exactly the same orbit as the Moon orbits the Earth, except that longitude angles measured in the orbit plane must be reduced by 180 degrees. For example, when the Earth is at the descending node and the XM axis points towards N, figure 2, the Moon is in reality at its ascending node, 180 degrees advanced from N. Therefore, the longitude of the ascending node and the mean longitude lambda must be reduced by 180 degrees when used in the Moon relative frame. The selenographic axis can be oriented to the selenocentric axis by means of the following four angles. 1. The true obliquity 2. To 180 degrees the longitude of the descending node 3. The inclination of the lunar equator to the ecliptic 4. 0. The angle measured in the lunar equator between the descending node and the Moon's prime meridian, where the Euler angles R and A are determined as functions of the orbital parameters 2, I and 0 by equating elements of the RUB and RLIB matrices. RLR, R dot 1, R dot 5. RL is look angle rotation matrix transformation from spacecraft body coordinate system to image coordinate system. RL can be further decomposed as RL is equal to RPO asterisk RMP, where RMP transforms coordinates from master reference cube MRC to payload cube PLC, and RPO transforms coordinates from payload cube to optical axis. RA is attitude rotation matrix transformation from orbital coordinate system to spacecraft body coordinate system, and it is given as a product of three rotations: pitch, roll and rear. Therefore, 2, 5, 4, 5. RA is equal to rear asterisk roll asterisk pitch. RA matrix is filled by using orbit to body quaternions in true of date reference system. Rho is orbit rotation matrix transformation from selenocentric coordinate system to orbital coordinate system. Estimation of ground coordinates from image coordinates process is exactly reverse of the above described computation process of image coordinates from ground coordinates. This is directly using the collinearity equations. As such, this is the solution of the look vector intersecting the lunar surface, ellipsoid. Space resection. Though the above described model satisfy the image ground-image relation, its accuracy depends on the exterior orientation, which may be poorer in many cases. Space resection is the process in which the orientation parameters are refined using a set of lunar control points, LCP. The updated orientation parameters are used for further data processing. The model is based on the collinearity equation, and the error in attitude is assumed to be systematic and follows certain polynomial behavior. Depending on the imaging condition, this systematic error can follow a higher order polynomial behavior, G second order or higher. However, the choice of higher order polynomial requires more number of control points, as the number of unknowns will be more. The polynomial coefficients are treated as unknown and thus are estimated using the lunar control points. A simultaneous least square adjustment is used to determine the most probable solution for the unknowns. The same way orbital parameters can also be estimated using the space resection approach. Rational polynomial coefficients, RPC, the rigorous sensor model of an image is used for transformation between the 3D object space and the 2D image space. It includes the physical parameters about the camera, such as focal length, principal point location, pixel size, lens distortions, and orientation parameters of the image such as position and attitude. The rational function model, RFM, is a general version of the polynomial model that can describe more complex ground-to-image transformations, which is generic in nature. It is otherwise called rational polynomial coefficients, RPC, model that is used as an alternative solution for the physical sensor model, and it is widely used whenever complex sensor model is not available. The RPC model forms the coordinates of the image point as ratios of the third-degree polynomials in the 2, 6, 7 coordinates of the world or object space or ground point. A set of images is given to determine the set of polynomial coefficients in the RPC model to minimize the error. The least square solution is used to estimate the RPC, 14, 15. Them generation to carry out them generation from a stereo pair or triplet imagery. Space resection will be carried out first, simultaneously taking any two images at a time out of three images of TMC using some control points taken from ULCN, Unified Lunar Control Network, or from Clementine reference. After space resection wherein orientation parameters are updated, traditional space intersection process will be used to generate the them, or compute the 3D coordinates, at the conjugate points, mass points, generated through image matching process between fore, aft and other imagery. Once the 3D locations of image points have been determined, the 3D points are interpolated using a triangle mesh interpolation. This mesh is then sampled at regular intervals in latitude and longitude. Vertical datum is based on spherical figure of the moon and a lunar radius of 1737400 m. All elevations thus generated are in meters and represent the true values as the input ULCN points. These calculations are performed under the IAU 2000 Cartesian coordinate alternatively. Bundle adjustment technique can also be considered for them generation taking all the three images of TMC simultaneously. Datum and map projection 7. 1. Moon shape parameters, moon ellipsoid or sphere and datum. The general shape of the moon is very nearly a perfect sphere, excluding local topography variations. In fact, the magnitude of the local topography variations is much larger than the overall flattening of the lunar poles or any ellipticity of the lunar equator. IAU-IAG 2000 report recommends using the same radius value for both the lunar equator and the lunar pole, a sphere. The lunar topography data are expressed relative to a sphere with the same radius as recommended by the IAU-IAG 2000 report. The values in the IAU-IAG 2000 report are listed below. Note: the radius recommended here is different than the reference radius for the LP150Q gravity field. Moon equator moon pole IAU-IAG is equal to 1737, 4 kilometers, radius of moon equator from 1737, 4 kilometers, radius of moon pole from IAU-IAG, F moon is equal to 0, 0, moon flattening factor, derived from IAU-IAG values, moon equator, moon pole, moon equator, 2, 7. Therefore, an average radius, 1737, 4 kilometers, datum shall be used for referencing topography data. 7. To map projections, simple cylindrical map projections are generally used for planetary mapping in addition to conic projections in middle and higher latitudes. The projections used on most published planetary and satellite map series of the USGS are combinations or variations of polar stereographic, Lambert conformal conic, and Mercator projections. 1 million scale maps and beyond were usually compiled on a transverse Mercator projection. But there were no fixed criteria for choosing a projection related to scale. A small number of special-purpose maps have been prepared on the Lambert azimuthal equilaria and the oblique stereographic projections. Maps published by the DMA have used similar projections in addition to mnemonic and orthographic projections. Use of the Mercator projection in equatorial sheets and the Lambert conformal conic in middle and higher latitudes is also followed. Polar coverage is usually portrayed through use of a polar stereographic projection between 80 degrees to 90 degrees north and south latitudes. Map projections chosen for Chandrayaan-1 TMC HYSI payload data correction and mapping are also in the similar lines discussed above. The map projections considered are 1. Mercator, general choice, 2. Transverse Mercator, equatorial and middle latitude regions, 3. Polar stereographic, polar regions, 8. Data processing with the development of the imaging model. A standard approach is followed for data processing to generate the radiometrically and geometrically corrected data product. First, the mappings from locations on object space, lunar surface or also called as output space, to locations in a satellite image, input image space, covering that area fully partially is carried out and this is stored as a grid file. This file is then used along with the raw data for resampling to generate a geometrically corrected image. Alternatively, the same task, product generation, can be done using RPCs along with the COTS package. The regular level 1 products, radiometrically corrected with only geometric tagging, no correction done, are generated through a software system developed at SAC, in an automated mode pipeline, 8, set up at Indian Space Science Data Center, ISSDC. The procedures are similar for TMC and HYSI, 2, 8.